Hello everyone. Welcome to lecture 5 of the course on reinforcement learning. I'm Dhiraj Madan and today we'll be looking at value iterations. So in the last few lectures, we had initially defined the idea of a Markov decision process. We had defined the notion of a policy and we had seen how to compute the value function corresponding to a given policy. So just to recap, a Markov decision process consists of a set of states, an action space. It consists of a reward function, discount factor, and the transition distributions. So the transition distributions and the rewards are governed by the environment, and the agent has the choice of choosing a given action at every time step. And the sequence of all the states, actions, and rewards that forms a trajectory. So you start from a given state S naught, the agent takes an action A naught, moves to the next state S1, takes an action A1, and so on. At every time step, whenever the agent moves to a new state, the agent also receives a reward from the environment. And all these transitions are governed by the environment. However, the agent can pick its corresponding action. The goal of the given agent is to maximize the cumulative reward, which is essentially an exponentially weighted sum of all the cumulative rewards in future. The agent needs to choose its action so as to be able to maximize this. The choice of action is called as policy. So policy is in the hand of agent. And one essentially needs to maximize this expectation, which is the expectation over both the policy and the environment's transitions of sum over t RT gamma to the power. Note that although the transitions are actually not in the agent's hands, but the policy is in the agent's hand, and the agent can now choose the policy or the actions so as to be able to maximize this expectation. In general, a policy can be both deterministic or stochastic, right? And we had seen that if you want to evaluate a given policy, let's say a deterministic policy, how do you do that? So essentially, we derive an equation which is known as the Bellman's equation. And essentially, what it says is that the value function for a given state, right, S is essentially the reward received at the state S plus gamma times the expectation over the next state S prime, the value function corresponding to the next state, which is V pi of S prime. So here we are assuming that the action chosen on state S is given by pi S, and this corresponds to a deterministic policy. However, later we also derived this same sort of value function corresponding to a stochastic policy as well, right? And we had seen that in general, this system of equations, it may not have a unique solution if gamma is 1. However, if gamma is strictly less than 1, right, and that also justifies the usage of discount factor, we are able to ensure that the system of equations has a unique solution, right? So first of all, it always has a solution, and then this is also unique. And in order to show that, we had used this fixed point theorem, and we had shown that the corresponding mapping from a given state to the new state, if one uses the iterative approach, that is a contractive mapping and contraction mapping, right? And essentially, for the case of stochastic policy, the equation is almost the same, except that one also averages over the choice of action for a given agent, right? So we are summing over this A naught pi of A naught given S naught, and then the equation is almost the same. And just to recap, in order to show the sort of existence and uniqueness of solutions, we had defined a sort of a iterative approach of the algorithm, wherein we initialize all the values to, let's say, 0. We could also initialize them to any arbitrary value, and then we perform the following iterates, wherein at every step we assign the new value function for a given state as Rs plus gamma times sum over S prime, P of S prime given S by S, and the value function corresponding to the state S prime, right? So this step is the one which will be repeated until convergence. And essentially now you have to compute the and we had shown that this algorithm in fact converges if gamma is less than 1, and it converges to essentially v pi of s. So that's what we had discussed in the last few lectures. And yeah, so there was also an optional video we did wherein we tried to prove the fixed point theorem, which we also used for proving the convergence of our iterative algorithm. And one thing I also want to emphasize, right, which I haven't made it very explicit, but I think many of you would have already understood that if we write down the Bellman equation for a given policy, okay. So the way that equation was written was as follows: was that we had this, v pi s is rs plus gamma times sum over s prime p of s prime given s pi s times v pi of s prime. So essentially this, okay, although we derived it formally, this actually has a intuitive interpretation as well, which I think many of you would have understood, but I'll just explicitly write it down. Essentially at a given state S, so on state S, you receive a reward, which is Rs, okay? And subsequent to the, after receiving this reward, we essentially can move to the next state S prime with this transition distribution, okay? So the distribution of S prime comes from the distribution P of S prime given S and pi S, right? And whichever state S prime I move to, the subsequent cumulative sum, right? So that's going to be gamma times v prime of s prime, right? Why? Because what essentially our value function, the way it's defined, is essentially r of s plus gamma times r of s1. So let's say the next state is s1 plus gamma square times r of s2 plus so on. So what I can do is that I can take out this gamma common, and essentially this corresponds to this expectation from S1 onwards will be V pi of S1, right? And if you average over all the possibilities of S1, which comes from the distribution P of S prime given S pi S, essentially your expectation is going to be sum over S prime, P of S prime given S pi S, V pi S prime, and this gamma, which is outside, and then RS is what is added. So actually one could have derived it in an intuitive manner, and actually what we followed was also something along these lines, but we wrote it more formally, right, when we derived that equation. So essentially on the state S, you receive a reward Rs, and after that the cumulative sum is gamma times the subsequent rewards which you accumulate after S1. So that's gamma times V pi of S1. And but S1 is averaged over this distribution P of S prime given S pi S. So essentially you need to average the V pi of S prime as well. So earlier we had derived it using more formal approach. We used the towering property of expectation, and then we sort of we splitted the expectation into two parts. So all that we have done, which is also the right approach, but then you should always have this intuition also in your mind. So that's what I wanted to point out. Today our goal is that how do I now maximize my policy? So how do we maximize with respect to policy pi, v pi of s? Okay, so how do we compute this? Right, and first of all, how do we also derive this optimal policy? That's also the goal. So firstly, we define something known as the optimal value function. Right. So earlier we had defined the value function corresponding to a given policy pi. What we can do is that we can also define an optimal value function. So I denote it as v star of s, okay, which is max over pi v pi of s. Okay. So essentially max over all policies pi, expectation over pi, sum over t, RT gamma to the power T. Given S naught is S. So the question is that how to compute this V star S. Okay. So one way is that, okay, we have seen how to evaluate a given policy. Okay. And now, if you are given a choice, then, how do you now optimize your policy to get this optimal value function V star S. One possibility could be that, you enumerate over all possible policies, but number of policies could be exponential, right? So just a question. So how many policies? Let's say deterministic policies from the set of states to actions. Well, for every state, I have mod A choices. So essentially, we have number of actions to the power of number of states. So it's essentially exponential in the number of states. And if the number of states is too large, or let's say, if the states is, let's say, uncountable, right? If you have a continuous state space, then, you can't even enumerate over. So how do we actually now compute this value function? So the idea is that we can use the same iterative approach, right? And in order to first do that, we'll first derive the set of Bellman equations for this optimal policy, right? For the optimal value function V star. So V star of S is essentially max over all possible policies, okay? Expectation over the policies and transition functions of sum over T, RT gamma to the power T, given S naught is S. Okay. Now again, as before, let me split this sum. Okay. So let's split this sum as two parts. So first of course we have R naught. So R naught is nothing but R of S, right? Because S naught is S. And then I have gamma times sum over T from 1 to infinity, RT gamma to the power T minus 1. Okay. Given S naught is S. Now R of S again I can take outside this expectation, right? And also I can take it outside the max also, right? Because RS is independent of our policy. So then I'll get this RS plus max over pi. Okay, and gamma also I can take outside the expectation and outside the max. So I can rewrite it as plus gamma times max over pi, expectation over pi, P of S prime given, okay. So when I say this P of S prime given AS, actually I haven't specified what is A and S, but essentially this is the transition distribution we are using. That's what we mean. So this is essentially the transition distribution. And then I have this sum over T from 1 to infinity, RT gamma to the power T minus 1 given S. Now note that in this particular summation, all the terms are from S1 onwards, right? All the terms are from T equals 1 onwards, right? So they depend on S1. So if I can condition on S1, then essentially I can get rid of S. So what we do is very similar to what we did earlier. So essentially we rewrite this expectation as follows. So we have max over pi. So essentially expectation over firstly, over the first choice of action we need to pick, which is pi of S, right? And P of S prime given pi S and S. Right? And then the expectation over the future sort of actions we pick. So essentially expectation over all the future actions and the future states. For T greater than equal to 1. And here essentially what I have is that expectation over A naught coming from pi of S, right? And S1 coming from P of S prime given A naught and S. So essentially I have this RT gamma to the power T minus 1 given S naught equals to S. And now, okay, so again I'm using the towering property of expectation. So this big expectation is essentially expectation over A naught and S1 and expectation over AT and ST for T greater than equal to 1. But in the inner expectation, I'll also need to condition on my A naught and S1. Right? So let's say S1 is S prime and A naught actually we won't need, right? Because once you conditioned on S1, then A naught, S naught, everything is immaterial. Okay. So essentially now even this max part, right? So this max part also we can essentially what we can do is that if you have to maximize this expectation of expectations, then essentially the inner expectation will also have to be maximized, and so and conditioned on that the outer expectation. So I can rewrite this as R of S plus gamma times max over the choice of A naught, expectation of A naught coming from pi of S and S prime, right, coming from P of S1 given A naught and S, or S prime given A naught and S. And then inside this, I maximize with respect to pi the expectation over all the future actions and all the future states for T greater than equal to 1. And the quantity which I have over here is sum over T RT gamma to the power T minus 1, given S1 is S prime. So note that S1 is S prime. So note that I had also conditioned on S naught and is S and A naught, but essentially we won't need that because once you condition on S1, then essentially by Markovian nature, everything else is immaterial, right? So essentially when we are defining a Markov decision process, if you want to look at the future states, then only the current state is important. The previous ones are not important. So now what is this max over pi expectation of AT-ST, for T greater than equal to 1, right? So essentially this sum is also R1 plus gamma R2 plus gamma square R3 and so on. So essentially this is the cumulative reward from time step 1 onwards. And if I maximize that with respect to the policies, so what I have is that I am actually looking at the V star from time step 1 onwards. And if I have conditioned on the fact that my state S1 is now S prime, so this is nothing but V prime of V star of S prime. So this quantity is nothing but V star of S prime. So what I have now is that, so what we have derived so far is that V star of S, okay, so that's R of S, okay, plus gamma times max over A naught, okay, of this expectation over A naught coming from pi S and S prime coming from P of S prime given A naught S of this quantity which is V star of S prime. Because if you maximize the rewards from time step 1 onwards, then you are essentially computing V star of S prime only. So essentially now the goal is, okay, so now it's very similar to what we had earlier, except that now there is a max over A naught, and this expectation I can compute as before as sum over S prime, P of S prime given A naught and S, V star of S prime. So this is what my V star of S is going to look like. So essentially this equation is now the Bellman equation for optimal value function V star. This is the set of Bellman's equation because you have no modest equation for modest states for optimal value. V star. Now, essentially, these equations are non-linear, right? Why? Because there is a max. So earlier, the difference from the earlier Bellman equation was that there was no max and A naught was just pi of S because we were evaluating the policy pi. Now we are maximizing with respect to the choice of the first action as well. So essentially, in order to get the optimal value function, and hence essentially this is non-linear. This is non-linear. Okay. So what I have is that V star of S is now equal to Rs plus gamma times S prime of P of S prime given it's max over A naught, S prime given A naught S and V star of S prime. So this is what we have, right, for all S. So there are modest equations, non-linear. These are not linear equations now. In modest variables. Okay. So how do we now sort of solve for these? Now the thing is that we can't use Gaussian elimination, and the only choice we have is to use the iterative approach again. So we again use the fixed point iterations. So essentially the way this is going to work is as follows. So what we have is the following. This is known as the value iteration algorithm for optimal policy. Or optimal value function. So the way it works is that, so you start from t equals to 0, okay, and BTS equals to 0 for all this. And then you have repeat until convergence. So essentially we need to update your so essentially we need to update as follows, that VT plus 1 star of S is essentially R of S plus gamma times max over A or A naught, sum over S prime, P of S prime given S and A, and V star of S prime, V star T of S. So this is V star T of S, which was initialized to 0, and then we have a way to compute V star T plus 1 from V star. So note that it is a very similar algorithm to the iterative algorithm we had for policy evaluation, except that we have a max over A here. Instead of just taking A to be pi of S, we are maximizing over the choice of actions. Right? So this is what we have. And yeah, T is T plus. So this is what we have. And now how do we ensure that, this converges? So we can use the same trick as before. So we define this mapping T, right, which maps, our value function at time step T to value function at time step T plus 1. So this is given by, the same equation over here. So essentially, so there is this particular mapping T such that Vt plus 1 star S equals to R of S plus gamma times max over A sum over S prime P of uh, S prime given A and S and B star of VT star. So basically, this is our sort of mapping. And the idea is that we need to show that. So the claim is that T is a contraction map. And in order to show that, essentially, we need to use one small result that, okay, so I'll come to that usage of that result. So essentially, let's try to show that first that this is a contraction. Right? So let's say we have two sort of these utility functions. Let's say u and v. Okay, and now let's look at the subnorm of u minus v. So which is a u prime minus v prime. Right. So let u prime equals to p of u and v prime equals to t of v. So this is essentially tu minus tv, the infinity norm, which is supremum of s, right? And then mod of tus minus tvs. And what is tus minus tvs? This is given by this. So essentially, this is supremum over s, r of s plus gamma times max over a, sum over s prime, p of s prime given as, okay, u of, okay, so this is vt star of s prime. Yeah. Okay, so this is what is tu, and similarly you have this tb, which is max over a sum over s prime, p of s prime given as, and b of s prime. And RS will get cancelled, and essentially you are left with supremum over s gamma times mod of max over a sum over s prime p of s prime given as, okay, u of s prime minus max over a sum over s prime p of s prime given as of v of s prime. And now there is a sort of a small result which you will need to prove. So I leave it as a homework exercise for you. So you need to show that for any okay, so for any two functions or two vectors, for any two functions f and g, what we have is that max over x, okay, fx minus max over x gx, the mod, is less than equal to max over x fx minus gx. So we need to show this. Okay, so this is something I'm leaving as a homework exercise. But if you now substitute this thing, right? So this becomes f of s and this becomes g of s. And we are maximizing both with respect to a and then taking the sort of difference. So this difference now is less than equal to supremum over s gamma times max over a, okay, of mod of sum over s prime p of s prime given as us prime, right? So this is my f of x and then minus g of x, right, which is sum over s prime p of s prime given a of s b of s prime. Okay, so essentially a, right? So they were choosing a different maximum of over a over here. Let's say some a1 and a2, and it was difficult to bound this sort of a difference. But if we use this sort of a result, that that differences of maximums is less than equal to maximum of mod of difference. So essentially that's what we have done. And now essentially the idea is that the sum over s prime can be combined, right? Because this max over a is the same a in both of these terms. And so I can rewrite it as less than equal to, okay, so gamma is also outside this supremum, and this is supremum over S, okay, and max over A, and sum over S prime, okay, P of S prime given AS, okay, and what I have over here is U of S prime minus V of S prime. And now I can rewrite this as, since P of S prime given AS, right? So all these terms are all non-negative. And essentially now what I can do is that I can apply triangular inequality, right? So that what I have over here is absolute value of a sum, which is less than equal to sum of the absolute value. And also P of S prime given AS is non-negative, so that absolute value of that is always the same as P of S prime given AS. So applying triangular inequality, I can rewrite it as P of S prime given AS times U of S prime minus V of S prime, and U of S prime minus V of S prime. This is essentially for all S prime, this is less than equal to infinite norm of Q minus V for all S prime, right? So essentially this is less than equal to gamma times supremum over S, max over A, sum over S prime, P of S prime given AS times the infinite norm of U minus V. Okay, and sum over S prime, P of S prime given AS is just going to be 1. And overall, this is going to be gamma times supremum over S, okay, of, okay, so max over A, although I'm taking, right, but this is essentially nothing but U minus V infinite now, because now this inner term inside this max is independent of A. So this is nothing but just this U minus V infinite norm, and it is also independent of S. So I don't have to even take that. So this is just less than equal to gamma times the U minus V. So that's it. So essentially, what we have shown is that for gamma less than 1, right, this is essentially a contraction mapping, because the infinite norm of U prime minus V prime is less than equal to gamma times infinite norm of U minus V, where gamma is less than 1. So essentially, this is a contraction mapping. For gamma less than 1. And once we know that this is a contraction mapping, then essentially there is not much to prove later. Essentially, we can use the same sort of argument earlier to show that firstly T has a fixed point, okay, and not just that, this iterative algorithm wherein we are iteratively applying the same operator T will converge to the fixed point of T. So the iterative algorithm converges to the fixed point of T. This is given by essentially V of V star of S is nothing but RS plus gamma times max over A, sum over S prime, P of S prime given AS, V star of S. Okay, so essentially this, which is the solution of Bellman's equation for optimal value function. So essentially the same iterative algorithm works. And one more thing is that, in both this and the iterative algorithm for policy evaluation, so I always write repeat until convergence. But what is the convergence condition? Right? So how do we determine that? So essentially, one way to look at is that, if the sort of the difference between the previous iterate and the current iterate, right? If Vt plus 1 minus Vt, that infinite term, right, which is the supremum over S, Vt plus 1s minus Vts. If this is less than, some threshold delta, right? So you can choose some threshold delta, and if the difference is not much, then you can consider that it has already converged. Okay. So thanks a lot. So this is what we have for today's lecture. In the next lecture, we'll see another algorithm for finding optimal sort of policy, which is known as policy iteration. And before that, I also wanted to discuss one thing. Okay, so basically, once you get the optimal value function, V star S, which is Rs plus gamma times max over A, sum over S prime, P of S prime given AS, V star S prime, right? So once you have determined V star S, how do you find the optimal policy, right? Because your goal is always to choose the best action. So let's say if you are in a given state S, right? What is the action which you should pick? Okay, so you should pick this particular action which maximizes the average value of the next state, right? So essentially, if you are in a given state S, so the action to pick is nothing but pi of S, which is pi star of S, which is argmax over A, sum over S prime, P of S prime given AS, B star of S. So once you have determined the optimal value function, you can always go to the optimal policy, right? And if you know the optimal policy, you can go back to the optimal value function because your V star is then going to be nothing but V of pi star. So if you know the optimal policy, you can determine the optimal value function by using the same set of Bellman equations for a given policy. If you know the given value function, you can determine the optimal policy using this argmax, right? Because in V star, you are going to pick this action. So essentially, this is also the optimal action. So that's what we had for today's lecture. In the next lecture, we are going to look at the idea of policy iteration. Okay. So thanks a lot. And yeah, take care. Bye.